Now let's start discussing model-agnostic methods. So for model-agnostic methods, there are two ways to go about it. So there's the global one and the local one. So for the global model-agnostic methods, it provides an overall view of how the model makes decisions across the entire dataset. And some examples of that would be permutation importance and partial dependence plots or PDPs. For the local one, it focuses on understanding individual predictions, providing insights into why the model made a specific prediction for a particular instance. And then, a very popular example of that would be Shapley additive explanations or SHAP. So let's now start tackling those examples. So for permutation importance, the impact is measured by randomly shuffling one feature's values and observing how much this disrupts the model's performance. So let's start with this original input data. You create a shuffled version of that. But of course, you train your model based on the original input data. Now you evaluate the original data. But for your trained model, you also evaluate the shuffled data, right? You see the values here that I've shuffled. And now you are comparing the score. So basically, again, we want to observe the disruption to the model's performance. And normally, we are expecting a decrease in performance by doing the shuffling. So that's how you measure the importance of a specific feature. Okay. Still quite straightforward, right? So this is like how it looks like when you visualize it. So you see like the mean values because you're going to be doing that many times, different shuffles, right? Different samples. And you see the spread here. So we used a box plot for this. So you see the mean here. So that's the average importance of each feature. Now, another example again is the partial dependence plots or PDPs. With this, we can visualize the relationship between the feature and the target. And it answers this question: how does changing one feature while keeping others the same affect the prediction? So it's kind of similar to hyperparameter tuning, wherein we have like a grid of values and then we test it out. Now, in this case, let's say the age feature, we have a grid of those values from 0 to 70, and we observe the effect on the performance by using different values. So as you can see here, it's not monotonically decreasing, but you can see there's a pattern that as you increase the age, the performance decreases. So this is for the Titanic data set. And already that in the Titanic data set, right, the older people have lower chances of surviving. So that's PDPs. So the examples earlier are the global model agnostic methods. Now SHAP or Shapley additive explanations is for local. And this is a very popular approach for explaining the contribution of all of the features to get to the output. So SHAP or Shapley additive explanations is based from the Shapley values concept in game theory. And the goal there is to properly attribute the correct payoffs to the different players in a game. So you have lots of players in a game, right? And you would want to understand how they contributed to the success of the team. And there's a mathematically rigorous way of calculating such, but we won't cover that in this session. But for applied purposes, basically what it gives us is this, how it got to the end result, which in this case is 0.96 or 96% certainty that this specific person or data point will survive. I also want to note the base value here, because like on average in this data set, this is the survival rate. But with all of these features that this specific person has, basically the chances of survival went up from the base value of about between 30 to 40% to 96%. Again, SHAP provides local explanations for individual predictions by showing the contribution of each feature to a model's output. So what I've shown is the visualization for a specific data point, but you could also visualize across multiple data points. Basically gives us an overall view on how different features affect the performance. So you see a plot here, and there's a guide that I've put here. So the vertical position indicates which feature it represents. The color shows whether that feature's value is high or low for the given row in the dataset. The horizontal position shows whether that feature's value contributes to a higher or lower prediction. So for example, for sex male, we see that generally, if it has a high value, then the impact on the prediction is basically the output is basically giving us lower chances of survival. So if you're male, basically, you have lower chances of surviving, right? For B class, if you have a high value here, you get lower chances of surviving. So for fair, if you have higher fair, you have higher chances of surviving. So that's SHAP, and that's it.